The hammerhead's secret sense is called electroreception, and it lets the shark detect a heartbeat hidden under solid sand from several feet away. It works through thousands of tiny jelly-filled pores called the ampullae of Lorenzini, spread across the surface of its head. These pores can detect electrical fields as weak as 5 billionths of a volt, generated naturally by the muscle contractions of any living animal. In most sharks, these pores are packed into a small area near the nose. But in hammerheads, the flattened, widened head, called a cephalofoil, spreads those same pores across a much larger surface, sometimes covering nearly 2 feet of width in the largest species. Researchers at the University of South Florida tested exactly how powerful this sense is by burying small electrical fields in sand, mimicking the signal of a hidden stingray. The hammerheads located the buried signal with a precision and speed that outperformed every other shark species tested in the same study, sweeping their heads side to side like a metal detector scanning the seafloor. That sweeping motion isn't random. A separate study published in the Journal of Experimental Biology used motion tracking cameras to analyze how hammerheads swim, and found that the wide head causes a side-to-side oscillation that increases the surface area scanning the seafloor in real time. The same researchers noted this scanning motion intensifies specifically when the shark is hunting close to the bottom, but disappears almost completely when it's just swimming through open water, proving it's a deliberate hunting tool, not a side effect of an odd body shape. The same head shape that powers this electric sense also fixes a problem every other shark has: blind spots. Most sharks have eyes on the sides of a narrow head, leaving large blind zones directly in front of and behind them. Hammerheads solved this by evolution, placing their eyes at the very edges of that wide head. A study published in the Journal of Comparative Physiology used imaging technology to measure the actual field of vision in live hammerheads, and found that several species have close to 360 degrees of vertical visual coverage, with only small blind spots directly ahead and directly behind. The same researchers found something nobody expected. Hammerheads also have overlapping stereo vision directly in front of their snout, which means they can judge distance and depth more precisely than most other sharks, despite a head shape that looks like it should spread vision apart instead of sharpening it. This sensory advantage turns directly into a hunting weapon. Researchers studying great hammerheads in the Bahamas filmed a specific technique where the shark uses the hard edge of its head to physically pin a stingray against the seafloor before delivering a killing bite. Stingrays are a primary food source for several hammerhead species, and many great hammerheads examined by scientists have been found with stingray barbs embedded in their jaws and mouths. In some documented cases, more than 50 healed wounds in a single shark, proof of how often this exact hunting method gets used over a hammerhead's lifetime, despite the physical cost. Not every hammerhead uses this sense the same way. Out of the 9 recognized species, the width of the cephalofoil varies dramatically, and that variation lines up directly with how each species hunts. The winghead shark has the widest head relative to body size of any shark on Earth, sometimes reaching half its total body length, and studies have linked this to an unusually large olfactory system, giving it the strongest sense of smell among all hammerheads. The great hammerhead, the largest of the 9 at up to 20 feet long, has a wide, nearly rectangular head built to maximize both electrical range and 360-degree vision while hunting across open sandy seafloors. On the opposite end, the bonnethead shark has a small, rounded, shovel-shaped head, the least extreme of all 9 species, and researchers found it relies far less on electroreception, instead surviving on a varied diet that, unusually for any shark, includes digesting seagrass as a real source of nutrients. Even before birth, this head shape is already taking form. Researchers studying hammerhead embryos found that during early development inside the mother, the head temporarily curls backward against the body, likely to fit inside the limited space of the womb, before straightening into the familiar hammer shape shortly before birth. This wasn't documented clearly until relatively recent embryonic studies, since hammerhead reproduction happens far from where scientists can easily observe it. Most hammerhead species are viviparous, meaning embryos develop inside the mother through a placental connection similar in function to a mammal's, an unusual trait among sharks that adds another layer to how this sensory head develops safely before the shark is even born. Despite carrying one of the most advanced sensory systems in the ocean, several hammerhead species are now critically endangered, largely because their fins are highly valued in the international fin trade, and their tendency to school in some species makes them easier to locate and catch in large numbers. Conservation researchers tracking great and scalloped hammerhead populations have recorded declines of more than 80% in some regions over the past few decades, a steep loss for a sense that took millions of years of evolution to perfect. If you want to see which shark species have actually killed humans and how rare those attacks really are, that video is linked right here.